I've got a slightly different talk for you guys. So it's going to be like 50% a science lesson and then 50% a Web3 DAOs conversation. And just show of hands, who's heard of ValleyDAO before? Obviously. Okay, cool. So we got a fairly neutral room here. So another show of hands, who's heard of synthetic biology? Even less people, right? So that shows you the kind of niche that we're dealing with at the moment, but it's definitely on the up. So just a bit of background about synthetic biology. Well, it's really focused on, it's an applied science, right? So it's using genetic engineering techniques and rational design of biological organisms to solve grand challenges in the world today. It's been, you know, if you've heard of biotechnology, it's not that far removed, but synthetic biology was kind of like the rebrand of biotechnology, and really like focusing on the fundamental design approach, building modules and things that we can then use in the same way that we use screws of a thread, right? Like these standardized tools make it easier to build more and more complex things. But I actually wanted to start today by giving a little bit of background on myself and why I got into this space in synthetic biology and why DAOs make sense for synthetic biology and for me personally. So my background, I did an undergraduate in microbiology at the University of Liverpool, and then I moved on to Imperial College and did a master's in synthetic systems and synthetic biology. Now, the systems part, surprisingly, ended up being the most interesting and part of the reason why DAOs are so fascinating to me today. Now, in systems biology, we look at the simple interactions between parts, right? And how they lead to more complex emergent properties of the system. So there's a lot of techniques and tools that we use to rationally and mathematically understand, we use a lot of mathematical tools and techniques to rationally understand and be able to then design these systems from the bottom up. But with DAOs, it's much the same, right? Like there are simple interactions, peer-to-peer, whether that's human-to-human or machine-to-machine interactions that can lead to more complex system property behaviors. And so I find that absolutely fascinating, right? Like if you've ever had a conversation with me, I'll probably at some point bring up ants, and I'm just fascinated by everything in biology that is distributed in nature. And biology fundamentally is distributed in nature, right? So does this clicker work? No. Where is next? Sorry. Okay. So we, in the synthetic biology space, and especially at ValleyDAO, talk about solarpunk, right? And the solarpunk movement is really a blend. It's a blend between technology and nature. And in synthetic biology, that's a very natural thought process, right? We see nature as technology, and we want to be able to use it to create a more sustainable and prosperous world for everyone. And we want to move towards a future of harmony. And essentially, we call it the three pillars of this harmony in solarpunk, which is nature, technology, and human civilization. So forming that perfect blend between the three that leads to very positive outcomes for everyone. But just talking about biology, as I said in general, that it's fundamentally distributed, right? Like the Earth itself is one giant biological system. Every single thing on this planet interacts with one another, and that leads to the complex emergent properties that we see on the planet today. So like one example of that is climate change, right? Climate change is happening because of the small interactions that we've had with each other and the effects that that's having emergently on the rest of the world. And obviously it's not a good thing, right? We want to start to move away from accidentally causing these massive emergent changes and starting to, again, rationally design emergent changes, but positive ones, right? We want to go backwards from climate change. We want to start removing carbon from the atmosphere. And the great thing about biology is that that was kind of where it all started. Biology is all carbon-based, right? So CO2 is the building block of almost everything you'll see in nature today. And that's amazing, right? Like, we want more nature, we want to bring back biodiversity, and we can do so with the carbon that we've got in the atmosphere. So it's a balance, right? It's a tipping point. But as I said, the amazing thing about biology is the fact that it's absolutely everywhere. It colonizes every square inch of the planet, and there's no environment too harsh. So think about the edges of a volcano, right? You would imagine not much living there. It's actually full of life. Little tiny microbes doing amazing chemistries. And what's amazing about these chemistries is that they do things that we didn't even think were physically possible, right? So we have all these different manufacturing and chemical processes, but biology just does it way better. It's much faster, it's much more efficient, it does it in a much more sustainable way, and it's integrated, right? Like, something sucks carbon from the atmosphere, and that process is circular. That organism dies, it returns to the atmosphere, or it returns to the soil, which then becomes something else. Nothing in biology is permanent, and I think that's kind of the magic of it, right? Like, it's fundamentally designed to build stuff up, build really impressive stuff, actually, and then, start over, run some new experiments, and create some really new and interesting things. So when we look at this pool of resources that we've got in biology and nature, it's vast, right? Like, all of the medicines that we produce today, well, 99% of them are coming from plants or natural sources, right? Or at least the processes to create them can be found in nature. And so every single chemical process that we can conceive, it's out there. Nature is doing it already. It's doing it in a more efficient way. It's more direct, and it uses enzymes to lower the activation energy of those reactions, make them more favorable, and yeah, just cleaner for everyone. I've not quite got the hang of this transitions yet. So one of our prolific figures in synthetic biology is George Church. And this is a quote from him. So he says, essentially everything that we can currently manufacture without biology, we'll eventually be able to manufacture with biology. And if you don't believe me, then I'm about to run through some examples of things that we can manufacture with biology that are just simply incredible. But as I said, synthetic biology is reimagining biology and using it in an applied way to solve global problems. So we take so we're inspired by nature, the pool of biodiversity and all of these amazing chemical reactions that we can see in nature, and then we take the building blocks, right, the genetic code that encodes for these reactions, and we can use those building blocks in new and interesting ways. We can start to cut and paste them together, create completely novel living cells, and then those cells can be used to take something from the atmosphere, a sustainable building block such as carbon dioxide or methane, as an input, and they can produce food, fuels, medicine, chemicals, pretty much everything that you need to sustain a civilization. And so that's something that I personally and most people in synthetic biology really want to see, is this explosion of doing things differently, doing things in a biological way that are more scalable and more sustainable. And so just to run through some of the applications, because this probably sounds like science fiction to a lot of you right now, right? But one of the amazing applications is chemical-free fertilizer, right? So if you know much about fertilizer, it's horrible for the planet. We currently produce it using the Haber process, which is incredibly pollutive. It's extremely unsustainable. And not only that, about 90% of the fertilizer we put onto the ground washes off. It goes into our water streams. It causes these algal blooms, which are a massive ecological disaster. So we're pumping so much energy and we're causing so much damage to produce this stuff, and 90% of it is literally being pissed down the drain. And it's expensive as well, right? Fertilizer is not cheap. So millions and millions of tons of it are going into the water systems every single day. And it's just a horribly unsustainable business. So one of the things that we're seeing with this project, Pivot Bioproven, it's a biological fertilizer. So rather than using chemical fertilizers, they've engineered organisms that have symbiosis with the plants, right? So these organisms, a lot of them found naturally in the soils, they interact with the plants directly. They take molecules that the plants produce, that they need to survive and proliferate, and they'll produce something in return. So it's a mutual exchange. So you can see already why you've got these peer-to-peer interactions that create very sustainable systems in biology. Ever wondered what woolly mammoth tastes like? So you may have heard about this. It's quite popular at the moment. It's animal-free meat. And it's an obvious one, right? Like, a lot of people here are vegan. A lot of people in the world are vegetarian, right? And a lot of people recognize that our current meat-eating practice is very unsustainable and damaging for the planet. And, you know, even if you don't care about that stuff, well, it's kind of cruel, right? Battery farming, it's horrible. These are living animals. We can't even verifiably say that they're not conscious, that they don't have sentience and feelings. But we're chucking them in cages and slaughtering them by the millions every single minute. But one of the really cool things that you can do with animal-free meats, and one of these companies that exists already in Australia, my undergrad supervisor actually went and worked for this company. They are producing exotic meats, right, as an entry point to the market. So woolly mammoth, things that you can't actually eat. Go and eat a rare, endangered species, right? Because some people are interested in that stuff. But if we can give them an avenue to try it, but not kill the animal and not make them extinct, then why wouldn't we, right? And to be honest, I'm quite curious what woolly mammoth tastes like. Now this one I love, self-replicating building blocks. So there's some obvious applications of biology, and then there's some less obvious, and I think these are the ones that are really special, the ones that just completely reimagine and rip apart our current model of how the world works. Now, imagine you can build a house, and that house builds another house, right? Sounds like science fiction again, but this is absolutely real. There are scientists currently working on building blocks that self-replicate. So they use sunlight, they will probably use CO2 and some of the minerals that are around them, and they will start to grow and divide. So in this particular paper, it's not a company yet, but they took 2 full bricks, grew them into 4, and 4 grew into 8. And it's not the fastest process yet. Like, there's still a lot of development that needs to be done to get this to any reasonable commercial scale. But wouldn't that be cool, right? Wouldn't that be cool? Xenobots. So this is another complete paradigm shift in biology. Self-replicating biological robots that can be used to do really cool stuff in the environment. So things like clean up pollution, repair the human body. So you may have heard of nanites or nanobots in science fiction movies, right? Like, these things are fucking real. And this particular researcher, Michael Levin from Tufts University, is really pushing this field forward. So they've engineered skin cells, removed a lot of the complexities that we have in our current bodies, and really simplified what they can do with them. But using these simple components in much the same way blockchains do, they've created this emergent system that can be used to solve a complex problem. So you can start to see why I like ants, and why that all makes sense for me is because ants are distributed too, right? They do the same thing. They're very simple, basic creatures. They don't have much individual capability. But put them together, and they can do some really interesting stuff. And another one, living materials. Imagine a jacket that changes color when you walk into a new room, or changes color when your blood glucose goes down if you're diabetic, right? Tattoo ink. This is a really cool one from Imperial, actually. One of my colleagues worked on this project. It's tattoo ink that changes color based on your blood glucose levels, or particular biomarkers for certain diseases, for example. So no longer do you have to prick your finger and do all this stuff that really no one wants to do. You just look at your arm and say, well, I should probably top up. But that's just one idea, right? Like, that's an obvious application of something that we would need, but we can also just do stuff because it's cool, like a jacket that changes color while you move around. And finally, this is a little bit less exciting, but it excites us in biology, right? In order to be able to do this really awesome stuff, and especially be able to do it in a very decentralized and fair way, well, we need to be able to do it everywhere. And at the moment, we can't do that everywhere. We do it in big labs that have millions of pounds worth of equipment, and they're not easy to access. You need particular qualifications. You need to usually be employed by the institution, and yeah, it's just a super high barrier to entry. But what some amazing people are doing in the synthetic biology space is lowering those barriers to entry. So working on the hardware that enables us to do things like print any gene, anywhere, anytime. So 3D printing, for example, like that was a game changer that really just exploded. This is the 3D printing of biology. No longer are you pipetting manually into test tubes. No longer are you having to check, did I put that one in? Did I not? Actually, I don't know. Run this experiment, get to the end and realize, oh shit, I did forget to put the DNA in. You can do it all with a machine now. Abstracts all of the complexity away. So you just drag and drop. You click, you select, and you create some really complex biology in a printer that fits on this desk, which is really fucking cool. And finally, something that really excites me is, and a project that we're actually working on collaborating with, is portable DIY bioreactors. So printing genes, similar thing. This is the 3D printing of cells, like creating cell cultures. So once you've got your genes, typically what you want to do is insert them into a cell, and then you want that cell to proliferate. And depending on what that cell does, you want it to proliferate in different ways, and the requirements that it needs are different. So you have these things called bioreactors. And bioreactors essentially give it all of the nutrition and environment that these cells need to thrive. But the problem is, bioreactors typically are very, very expensive. There's a huge amount of patents on all of the technology that just make it impossible for you to do anything without forking out at least 20K. And that's just for like a desktop one. It really shouldn't be that expensive. So what these amazing people are working on is the Raspberry Pi equivalent of a bioreactor. So getting it into people's hands so they can start to design their own bioreactor systems. So they've got these bags, right, that are laser glued together. So you get two sheets, and this laser comes along, basically glues these pockets together, creates these patterns, so you can have these different geometries in your bioreactor system. You can have different compartments for different chemicals. You can add pumps, different modules, and you can connect everything up together. So you can build your own bioreactor system completely bespoke, but do it in a way that's super, super cheap. I mean, plastic, obviously, inexpensive, and laser processing of that is also inexpensive. But amazing, right? But why isn't it taking off? Like, why are we not seeing this stuff in our homes today? And the problem is really in three areas, I think. It's the inefficient funding systems that are driving this innovation forward. But then there's also the middle step. There's the lack of translation of that research. Most of it is happening in academic institutions, and there's just not a ton of incentive for them to spin out and create things that are going to benefit the people. So there's a huge ton of technology, like, for example, those self-replicating building blocks. But you know, there is no demand for things like that at the moment. There's no market for a house that builds itself at the moment because no one's even thought about it. So how do we use that to create a sustainable and successful business? And then finally, I think one of the biggest problems, and Chris really nicely touched upon this yesterday, is the IP landscape. The technology is heavily protected, and we have what I like to call these technology islands, right? The incentive at the moment is, I develop something, it's my invention, I want to benefit from it, so I'm going to patent that, I'm not going to let anyone else touch it, and I'm going to build a business from it. Great. Great for me, great for my business, great for the, I don't know, less than 1% of the population that are ever going to interact with my business. But what about everyone else? And when you're building things that are so fundamentally necessary and impactful, I personally believe that these should be in everybody's hands, right? We shouldn't be protecting them. We should be getting them out there as much as possible, especially at these early stages when we're still innovating, we're still building on top of things. We want people to play with it. We want people to do things that we didn't predict them to do with it, so that we can see novel developments and really accelerate the innovation cycle of this ecosystem. So just zooming in on some of those problems a little bit, research phase, right? So painfully slow to get funding received, and it's a closed box, right? So there's a small group of people that review your application, and typically, you know, they're the same cohort of people, they're all friends, they've all worked with each other, and what you actually see is a lot of them awarding these grants to each other, right? Like it's a closed circle. It's an elite society of academics, and that's not what academia should be. So you get a lot of bias in that, right? Like if it's a small group of people, then much easier to sway them one way or the other on a decision, and especially when money is involved. And then it's unsustainable, right? So a lot of the funding models in science rely on public money or philanthropy, which is great for getting things off the ground, for doing high-risk stuff. But then when that technology is being like patented and spun out, well, technically, I as a taxpayer have paid for some of that, then I'm being paywalled to even access it. So, that just doesn't philosophically align. And so if we want to develop commercial technologies, well, we should be exploring a little bit more on the private funding side. And you'd be surprised, despite there being way more money in the private sector for science, that most of the money on the early stage stuff is coming from public money. So then the translational phase, right? So what do I do now? I've got my technology. What do I do with it? Well, scientists are great at certain things. They're great at science, but that's one reality, right? Business is a very different beast. So there's limited know-how from the scientists on how to commercialize their technology. What are the essential things that I need to understand to create a successful business? Even though my technology might be super impactful, a lot of these technologies and companies have failed purely because of the business, right? And we don't want to see that anymore, right? If we've got something that's really impactful, then it should reach people regardless of the business needs. And then, so there's finding a team, right? If I'm not the expert and the one that's going to be able to take this forward commercially, then I need to find someone that can. Where do I find that? All of my friends, my professional network, are academics. I hang out with them at the weekends. Like, these aren't the people that are going to be bringing that business expertise. I can go and network with people, but that's time consuming, it's difficult, and 9 times out of 10, they're not going to be the right person. Even if they've got the skills, I just might not vibe with them, right? And then finally, typo there, that should be number 3, but we've got a lack of motivation. Some scientists just don't want to do like commercial stuff. They just want to do science, right? You get into science because you're curious, and most people in academia recognize they're not going to be millionaires. So you've made a decision to choose curiosity over usually financial stability or prosperity. But I personally don't believe it should be that way. There shouldn't be a choice between those two things. So if scientists want to do science, great, let them. They're amazing at it, and we want them to keep doing that. But let's give them some helping hand in realizing the benefits from their technology. And so, kind of already covered this, but industry, right? The incentive is don't touch my IP. So there's about, I think it's over 99% of all patents never even recoup the cost of filing the patent. So we've just patented everything, and no one's even using it. Like, no, it is ridiculous. And so, like, what do we do with that? And this is where I think decentralized science has a really interesting role to play. There's all this technology out there that's just waiting to be used and explored. And if we can convince people to allow us to do that, then we could see some really magical stuff. So ValleyDAO, what are we doing? Well, we're rethinking the research translation process. So we're using a community-powered approach, and this is where it becomes a little bit different from your typical crypto project, right? Because most of what we do and most of the system that we're working with is human, so it's much less predictable. We can't just order machine to do certain things. We have to work with some level of uncertainty of how people are going to interact with each other. But, and as I was saying to some of my colleagues yesterday, I believe the magic is in the chaos, right? So you put all these amazing people and minds together, and it's like a melting pot, right? There's all this energy, there's all this buzz, and there's different pathways to reach certain end points. So I might know someone in my network that's an expert in this. They might know someone that's an expert in the other thing that I need. And suddenly all of the stars align that enabled me to reach my dream. So, you see this network graph. Well, what I actually see it as is a pathway, a possible map of pathways to a certain outcome. And when you have connections between every single person rather than, centralized systems where groups of people are connected only to a single institution, there's only one pathway for those guys, right? but in this system, there's millions of hypothetical pathways. And I think that de-risks, to a certain extent, some of the complexities of spinning out the research. So we are a decentralized autonomous organization, although that's up for debate. I don't think there's any real DAOs out there yet. But we are really focused on like the governance process, right? So we let members decide the direction of the DAO, key decisions, but also particularly which projects we fund. So now we don't have this small cohort of people making the decisions and calling the shots. And incentive alignment, right? So what can we do to bring these people together in new and interesting ways? What can we do to change the current landscape, the current incentives, and just foster a more exciting and innovative ecosystem? And then the real magic, right? Pooling of capital, resources, and network. The three like major value that we all have as scientists, and we don't even know it, right? We are literally being exploited by academic institutions, by VCs, right? They know the value we have. Scientists create, I think, over 90% of all of the value in the entire economy. So they know this, but scientists don't recognize this, right? As I said, we're choosing to be broke and curious rather than, you know, really benefit from the impact we're creating in the world. So we want to lower those barriers to entry and really allow this ecosystem to recognize its value, that it is independent of an institution. We have all of this stuff. We don't need them. Of course, we need a lab, but we can build that. So also, we are promoting fair IP sharing, and this is where our partnership with Molecule is especially relevant. So we are looking at using IP NFTs as a new incentive to promote collaboration in synthetic biology research, and I'll get into that a little bit more in a second. So just a look at our growth cycle. So ValleyDAO is leveraging the network, as I said, of its diverse expertise, of its community, to source, de-risk, and then commercialize those projects. So another major benefit of this network is, well, I just have exposure to so much stuff that's going on around the world. And if I have that exposure, then I can see opportunities much earlier than most people. And that's very lucrative for investors, right? I want to get in early on these potential unicorn companies, which is great for them, but, you know, again, they're going to extract all of the value from that. So what do? Well, we've got ValleyDAO, right? So this is the consortium of synthetic biology researchers around the world, and rather than that value go back to, you know, small groups of individuals, it goes back to the entire ecosystem. So we redistribute it to the community. And that's not redistributing profits to the community, that's redistributing the governance of that value creation. So now we've got a treasury, we can fund and translate and support research, but we can also grow that treasury, and then we can continue the growth cycle. We can fund, translate, and support new research. So you can see why this seems like a much more sustainable business model than just funneling public money into research and most of it not really going anywhere. But what's really important to us as well is that the researchers themselves benefit. So, you know, they get proceeds and equity as well from whatever is created. Now, either we take the IP off their hands and we spin it out ourselves, or they become an integral part of that process. They can become a founder if that's what they wish to do. And we will support them through that process as a community. And instead, we'll take, rather than owning the IP as a community, we will take equity in the company for our contributions. And so how do we actually achieve this? And this is something we're still, you know, working on every day. People stuff is hard, right? Like coordinating groups of people is amazingly difficult, especially when you're trying to balance the chaos. And so we have some structure, we have some hierarchy, of course, and that's just to keep things moving, otherwise nothing would get done, right? So we have a team of original growers, of which I am one of them, but we have 4 more, and they are essentially growth group leads. So we have these different work groups. The 3 main ones are displayed there on the lower half of that graphic. And these leads will lead these growth groups that have, you know, a certain number of people in them, and these people will, you know, have different responsibilities within those growth groups. And so, but those leaders are community elected. So although, you know, there was a small group of people that started this project, well, we're probably not going to be the ones that end this project, and we're okay with that. You know, we didn't set this up so that, you know, we could be the kings of the SynBio ecosystem. We set this up so everybody could be the king of the SynBio ecosystem. And so what do the growth groups do? Well, governance, obvious one, right, is focusing on the decision-making processes, proposal writing, defining the constitution of this ecosystem, and then facilitating the mechanics of that, right? How do we actually enable the governance process? How do we make it more fair for everyone involved? Then we've got communications. Again, obvious one. We need to publicly engage, otherwise no one's going to know what we do. So that's why I'm here today, right? So we have a growth group that is purely focused on the public interaction and growing that synthetic biology community, which is a really important part, and something that, you know, despite all of the commercial opportunity here, there's a huge opportunity to create a community. You go out and speak to a lot of researchers working in a very niche field, and they're like, oh yeah, cool, I've got like 5 friends that do this. Well, there's actually like 5,000 people around the world that are also interested in this, but you just don't have exposure to them. So forming these online digital communities enables us to do that in a much more scalable way. And then we've got deal flow and incubation, which is focused on the commercial aspect. So scouting, sourcing those deals, forming partnerships, and spinning out that research. But we're also launching 2 new growth groups. And as we've grown our community from the bottom up, we're still relatively small, about 1,000 people in our Discord, which doesn't sound like much, but there's actually not that many SynBio researchers still. But our priorities are starting to shift a little bit. So we've recently launched our token called the Grow token. And now we've got a community. Now we can start to play with our community. We can start to change the incentive mechanisms. So one of those growth groups is the ecosystem/tokenomics growth group, which is focused on identifying all of the different agents in our system and how can we get them to do the things that, you know, are ultimately going to benefit the ecosystem. So things like setting objectives, as I said, identifying those agents, modeling those mathematically, right? Defining the constraints and the dependencies of the ecosystem, and just taking this whole systems mindset that synthetic biologists are using every day in the lab, but applying that to the science of the science, meta-science, right? And then there's testing and deployment, monitoring and adjusting, which has to be a continuous process, right? If we're creating this dynamic ecosystem that we want to be self-regulated, then we need to continuously test, monitor, and make sure that it's actually doing what we designed it to do. And then we've got the product growth group. So IP is great, but it's a long-term strategy, right? IP value, as Chris said yesterday, it's hard to define in the early days. No one knows how much potential a certain technology has until it really hits the world running. And so what the product growth group is doing at the moment is focusing on customer discovery to explore new revenue generating opportunities for the DAO. Things that we can do in the short term, like software and services that can, you know, and keep us afloat while we start to accrue these assets in IP and fund really impactful research. But I think one of the amazing things, again, about this community approach is that we've got a rapid and wide platform for product development. Again, we have so much exposure to so many stakeholders across the ecosystem, whether they be the scientists themselves, but also investors, entrepreneurs, AI engineers, right? So we're starting to connect all of the nodes, and that's a huge opportunity for product development. We've got a platform that we can just test stuff on people that are really keen to test stuff, and do so in a way that they are benefiting from that directly as well. And so this is a quick look at some of our flagship projects that we're working on at the moment. So we have a collaboration that we are just finalizing now with Imperial College London for the sustainable production of palm oil. So engineering microbes to be able to synthesize oils that everybody knows, right? Palm oil is hugely disruptive industry. And there's massive amounts of deforestation, particularly in the Amazon rainforest, to produce this stuff. But if we can produce that in a machine with cells that are using CO2 from the atmosphere, well, that would be much nicer, right? Then there's high-performance fluorinated biomaterials. Now, if you don't know, fluorinated compounds are absolutely everywhere. So fluorine is added to to improve some of the properties of these materials, but it's actually really toxic and damaging. So a lot of these fluorinated materials, well, they degrade, they end up in our water systems, and it's a public health risk. Not only that, we have no idea what impact that's having on the microbiomes and biodiversity of the planet as well. So producing them biologically, not only can we produce them in a cleaner way, but we can also degrade them much easier because we've built them from sustainable building blocks. Then one that I'm really excited about is ChatGPT for SynBio. So imagine, again, abstracting all of that away, just sending in some text prompts, design me a cell that sucks out carbon dioxide and makes me steak. And then it just does it, right? Sends that file to the DNA printer, runs a ton of parallel experiments, maybe one out of those 100 worked, and now I have something. And I could have got that in hours instead of years, sometimes this stuff takes. And then just some others that we're exploring at the moment down the bottom. So synthetic biology collaboration in space with NASA Ames, open source DIY bioreactors, which I obviously already talked about, and then some collaborations with other stakeholders in the industry as well. And just to zoom in on this project in particular, well, there's actually opportunity to generate a wide range of IP. Now, we're not just talking about the process, we're also talking about the cells themselves. We're also talking about the genetic engineering tools that enable us to rationally design these things. So there's lots of IP potential, and you can see why the current incentive just makes it horrible for anyone to innovate, because, yeah, I'm going to patent all this stuff and no one else can do it. And although I'm applying it in this particular application, a lot of this stuff has parallel applications. So it could be beneficial for totally different projects, but they still can't touch it because it's my patent. So with these community-owned patents, rather than single companies and stakeholders being able to benefit from that, we can enable and incentivize people to share that IP, to collaborate, to co-develop, and everybody benefit from that ecosystem. But what's really impressive about this project is the way in which that they're producing this. So currently, we already we have the capabilities to produce these sustainable palm oils, but it's just really expensive. It's never going to compete with a commodity. So we need to drastically decrease costs, which means we need to drastically increase the innovation cycle, which is just stagnating at the moment. And then so this is one of our academic spin-out successes. So this company from, this team from Denmark Technical University, we helped them recruit their own corporate team. We sourced the project obviously from the community, and we are helping them apply to the Bioinnovation Institute for 500K in funding. So this is an example of technology that was already developed that we didn't necessarily fund, but we helped them in this process, and in return we've got a 5% equity agreement with them in that company. Now, this is amazing because it didn't really cost us anything, other than time, other than our intangible assets that we have as a scientific community, or not just a scientific community, but a synthetic biology community. And then there's this one as well, who are currently applying to YC and are raising a 10 million valuation. We've only been around for, let's say, just over a year, but really only having traction for the last, I'd say, 8 to 12 months. And so it might not seem like a lot, but we've been able to do some really impressive stuff with very limited resources. So imagine once we scale the impact that we can have as an ecosystem. Well, we've got an experienced and complementary core team. So I mentioned the original growers. Obviously, there's me up there. I had longer hair. Albert, he's the core lead and also leading deal flow, along with Dan Hussey, who currently works at the University of Texas in the tech transfer office. We've got Hamza as well, who's our governance king and operations specialist. So he's the lubricant that enables us to do all of the things that we want to do. And then Nicole, who we've recently just joined us. This is just a snapshot of our community. There's way more people, obviously, but this just shows you the vastness of the touch points that we have, right? We have exposure now to Stanford, University of Westminster, Berkeley, Imperial College London, and so we've got all these different touch points now that we can source deals, but we can also connect all of the different people that we need to connect in order to make these things a success. So it's no longer linear, right? There's, as I said at the beginning, these multiple possible pathways So each person brings their own network, and put those networks together, you've got some really cool network effects. And I'm running out of time, so I'm just going to rush through this last bit. But we've just recently partnered with True Ventures, who have given us a $300K contribution, and they have an amazing community as well. Not only that, they have an amazing portfolio and all of these different companies across SynBio, but also crypto as well. So we're now part of this amazing community inside our community. Love it. But we also raised an additional $363K from our community. So this was a crowdsourcing for the token. We sold 3.5% of total supply on a Gnosis auction for a final grow price of around $0.1 per grow. So our total raised is about 663 in Q2 2023, and we have plans to raise much more because it doesn't really go far when you're funding expensive research. Now, if any of what I've told you today interests you, then you can scan this QR code. It will take you to our website, and then you can find straight away the link to hop into our Discord. Would love to see you all there. Please just introduce yourself. I usually will welcome you, but one of our amazing team will also will be able to help you find your place and where you can contribute within the DAO. So thank you very much for listening and your patience on this very hot Sunday. And if you have any questions, then please don't hesitate to ask. Thank you.